Good afternoon, everyone. Welcome to Bilkent University Library Art Gallery for the third and final Library Lunchtime Lecture of this semester, and the last one for this year as well. So I weep a little tear at the end of the exciting series. Today our speaker, Professor Ömer Dağ from Chemistry, will shortly be telling us about a fourth phase of matter, liquid crystals. When I was at school, which is more years ago than I wish to remember, we were told there were three states or phases of matter. So I'm very excited to find out that my chemistry teachers were wrong all those years ago, perhaps, or something like that. We'll see. I'm obviously not in contact with them anymore. I was very bad at chemistry at high school, so I look forward to doing my best to understand what Ömer has to say today. Professor Ömer Dağ graduated Bachelor's of Science from METU, Middle East Technical University, and he also followed his master's and doctoral studies there. He subsequently went to the University of Toronto in Canada to do some work and also as a postdoctoral researcher. And in 1999 he joined Bilkent University, where he's been ever since. I had a couple of interesting points to add about his work. He's told me that some of the materials, porous materials that he and his groups have worked on were synthesized in microgravity conditions in the Space Shuttle Endeavour 77. But he's added it was not the time it exploded and blew up. So it's nothing to do with Professor Dağ that disaster happened. His research involves nanomaterials, lyotropic liquid crystals and mesoporous materials, which I hope we'll find out about some of those now. He's published numerous articles in very prestigious citation index journals, and in the SCI citation lists he's received over 1,000 citations, which is very impressive. He's also received awards from Tubitak and Tuba for his research. Like with many scientists, of course, it's not the work of one man, but the work of a man or lady, of course, and their team, which is very important. Something very different from what we do in history in my department, where we tend to be a little bit more isolated. So I'm sure a lot of what we'll hear about today is Professor Dağ's work, but the work of his team in that respect as well. Okay, I shall be quiet and let our speaker take over.
Okay, thank you. Thank you, Dave. Thank you for coming. I will try to explain this fourth phase of matter, and towards the end I will try to entertain you a little bit, and towards the end I will talk about what we do in Bilkent. Like matter, when you look at, as David said in high school, we look at three phases of matter: solid, liquid, and gas phase, that we always deal with in nature. We are always exposed to these materials, basically. Solid materials, like right now we are sitting on some of those. Gas we breathe basically, oxygen, that's the life. And we constantly get exposed to those three phases of matter. But the fourth phase is not very common. But we daily use, but we really never notice what they are. Okay, like on TVs, LCD TVs, you deal with liquid crystals. Like our computer monitors are made by these fourth phase of matter. Anyway, let us start. This field was discovered those years, 1888. When I look at the history of science, this always this number pops out. Apparently they were working really hard on those days, and I have seen many important discoveries on those days. He's a botanist, this Reinitz Ezer, who discovered this, and he was working on carrots at the time. And they discovered that they extracted some organic compound, and this is a solid to start with. When he was heating to determine its melting point, he realized there is more than one melting. It wasn't melting like any regular solid materials. They were going into semi-solid stage and then going into this clear liquid phase. And at the time, he didn't really name the field, but later I will give you a brief history on that. It is this is the molecule that he discovered at the time, showing this liquid crystalline phase. This phase has two important areas. This thermotropic liquid crystals. This is the one we use in computers and electronics, basically. I have no interest and no work on that part of the field. I mostly work on lyotropic liquid crystals. As I said, this phase is in between solid and liquid. Like when you look at the arrangement of molecules, if you take these as a single molecule or atom or whatever, in solid, they are all well-oriented and well-spaced. They are regular. Everything is perfect almost, except like when you look at details, of course, there is no perfect. Nothing is perfect. But compared to those two stages, these are perfectly aligned, perfectly located. When you do like certain measurement, you can locate the position of these molecules. And if you look at the liquids, on the other hand, everything is random. Nothing is fixed. Everything is tumbling, rotating. Like this thermal energy is good enough to make these molecules not stay in one position, move around. Okay? Completely random. And this phase is in between. Like when you look at the shape, some like on average they are aligned in certain direction, but some are tilted, some are like in different orientation. And there is basically behavior of this phase is exactly in between those two. Some solid behavior you will see, like I will show you some data, and some liquidic behavior. That's why it is named liquid crystals. And most of the time, like liquid crystal, mesophase, they are both referring the same thing. Basically, liquid is liquid, crystal is a behavior solid, and the name comes from a combination of those two. Mesophase, when I say, this is solid phase, this is liquid phase, this is in between. Meso means in between, basically. Okay? Like that's why sometimes I will say mesophase, sometimes I will say liquid crystal. They mean the same thing, basically. Thermotropic liquid crystals, basically they are some kind of molecules, like this is one of the key, have some shape. Some are rods, like this. Like if you look at this molecule, these corners are all carbon. You have the cyanide group here. You have an alkyl group there. This is an organic molecule, basically. Shape of this molecule is rod-like. This molecule is basically rotating constantly in this axis. It looks like a rod, basically. And some molecules are disc-like, this shape. So they can basically align with respect to each other in a way to form this phase. And some are like exactly like banana. That's why it is called banana-shaped molecules. Thermotropic liquid crystals are widely used in displays of low energy cost in many sensory applications. This field is the one, basically more exciting maybe, but the field that we work is a little bit more boring, but there's more chemistry there than this. Because here the chemistry is just to synthesize these molecules. Like there is an organic chemistry behind these molecules. You have to synthesize, and not every organic molecules will show this behavior. Maybe like very few molecules have this property. Most organic compounds, they are either like they can be solid. When you heat it up, it melts. Okay? And the thermotropic phases, maybe I have somewhere here, show this behavior. When you heat, temperature is important and pressure is important. Basically, you have a single molecule that goes from solid phase to liquid crystalline phase, and you can use this phase for certain purposes. I just gave a list of different type of liquid crystals. This group is all named nematic liquid crystals. When you look at the, like if you look at each one of those like elongated shape as a single molecule, somehow they are aligned in one direction. They are not just random, they are aligned. They are random along this axis, but all aligned somehow in certain direction. And that direction I will call it director. Maybe later I will use a little bit. Like there is a lot of randomness in the other axes. If you have some order, like those, these are quite aligned. as well as they are evenly spaced. They look like layers in a way. These type of liquid crystals are called symmetric phase. Okay? And like when you see more order, which means more like a lot of forces making these structures to stay like that. That requires more energy, basically. Like to melt those, maybe you don't need to get to this phase, you don't need high temperature, but maybe for those, you need a little bit higher temperature to get into this liquid crystalline phase. That's why you cannot use every liquid crystal, like every molecule which shows liquid crystalline behavior in those liquid crystal displays and everything. Okay? They have to show this behavior at around room temperature, basically. Okay? Otherwise, there is no use. Again, this nematic phase is the most common one used in these displays. Again, I am just showing these rods are like certain alignment. That alignment is good enough. Later, I will show you what I mean by. Again, these plates, again, all the plates are pointing, looking in one direction. They are not just random. They are slightly aligned. That plays the trick when you deal with light, basically. And to characterize these materials, one of the most common technique is polarized optical microscopy. Another one, X-ray diffraction, like I will give you one example from each. Another is differential scanning colorimetry. In addition to many other techniques, like in chemistry, we use various techniques. You can use all these techniques, but these three techniques, simple, easy to use, to decide if you have a liquid crystalline phase or not. In this microscope, this is a light microscope. Basically, light comes out from this site, and you have a polarizer here. You have a sample there, and you have an analyzer there. These polarizers and analyzers does the trick, actually. Light goes into this polarizer. It lets certain light go through this polarizer. These are, I don't know, like you all use sunglasses. Some are Polaroid. If you look at your, like if your computer screen is made by LCD, if you look at with certain angle, you see nothing. If you rotate your LCD screen, you see everything. Okay? Orientation of these are extremely important if you have a Polaroid sunglasses. Anyway, so this does the trick, basically. It lets certain polarized light go through this polarizer. It is a kind of polymer, basically. It just like filters out all other components. And if you have the liquid crystal sample in between, and if this liquid crystal have two different refractive index because of these orientation and everything, then it can change the polarization of this light. In a way, this analyzer is perpendicular. If this sample is doing nothing, basically, it comes out with this polarization, and on this analyzer, it gets stuck. You see nothing, basically. You see dark. Nothing goes through. Only time you see something after analyzer is your sample has to do something. And this something comes from refractive index, basically. These materials, if they have more than one refractive index, they can do this trick. Otherwise, they will just like go through and nothing will come out. And those type of materials which has single refractive index, simply you can picture as all amorphous materials like glass, all liquid materials, they are all isotropic, I will call it isotropic. And anything which has more than one refractive index are called anisotropic. Anisotropic materials can do this trick, basically. You can see something out. That's the whole principle of all these LCD, all these displays, basically. There is light or no light. It's based on, like in electronics, you have 0 and 1. You can establish the whole electronics. Here you have, yes, you have light or no light. Okay, these two basically determines the whole trick. And this is the refractive index basically of these type of materials. If you have two different refractive index, when you heat the sample, this is the temperature axis, at some point, when your liquid crystal melts, it becomes a single refractive index. Basically, This cannot distinguish the light, but this can distinguish the light. In a way, you see something at the end. I give you, like, this is the, under the microscope, if you have an anisotropic liquid crystal material, you see some sort of a texture. This is related to what is really going on in there, but you see something bright in there, some color, some image. When you heat and melt, you go to dark stage. And in liquid crystal display, basically you are switching between those two, dark versus light. Okay? And X-ray diffraction, again, works with the principle of this Brock's equation. And they diffract at very small angles, just because these repeating units are quite large. Like, I will not really go into detail, but everything in liquid crystal field, all the diffractions are at very, very small angle. Everything, when you look at the solid, all the diffractions are at very high angles. When you see diffraction at small angles, you know you're dealing with something like these type of materials. Plus, physically, you can tell. When you touch them, they are soft, extremely soft material, like gels, okay? But they have certain orientation, certain structure in there. They are not random. That's why you see diffraction. If they are random, you will see nothing, basically. Like when you see these diffraction, you can use this equation and index all these and determine how they are staying, what the distance is between them. You can get lots of detail from these measurements. And DSC, thermal differential scanning colorimetry, also thermally tells you if you have this phase transition, it gives you signals, basically. And the position of those signals are telling you at what temperature range your liquid crystal is behaving as liquid crystals. Okay? And for application, you don't want your liquid crystal to become liquid crystal at 60 degrees. You want something in this range, basically. Something like working room temperature range. That's why not every molecule is doing the trick, but certain type of molecules are useful. Yes. Let us look at the history, how this field developed. These are mostly thermotropic. Everything, like in the whole history, is mainly on thermotropic, but later I will give you some on lyotropic ones. First discovered, as I mentioned, in 1888. Later, it is named as liquid crystal by Lehmann. His first publication, 1904. And then later, basically, this is maybe the first step. This person basically did the first experiment, put this liquid crystal in between two plates, basically. That's the start of everything, basically. And later, the structural details are found out, and by Friedel, this field, these materials are classified in three types: nematics, basically mostly random molecules; symmetrics, you have a little bit more order; cholestric, you will like, these are also important group of thermotropic liquid crystals, such that these orientation, like these molecules are usually chiral. In a way, these orientation basically repeats itself after certain distance. In a way, they diffract or reflect light at visible region. And like if those type of cholestric phases, even though these materials are colorless, you can see sharp colors. You can see blue, red, depending on that distance that I am talking about. And later, basically first maybe device is made in 1927, and it was patented by this company. And first book came out in 1962, almost after a century later, first English written textbook. And later, they found out there is an electro-optical effects, like this is probably the beginning of those display technologies, that under electric field, these, when you apply voltage, you can play with the alignment of these molecules. In a way, you can make the light go through or no go through, basically. You can play with this alignment in a way. You can switch the light on and off using the little bit voltage there. And later, like this color material, Hale-Meyer, and this is the invention of LCDs. And like after that point, I mean, these are all details, like a lot of companies start getting involved and doing business. In a way, all these active matrices are made, and all these Samsung, all those electronic companies are getting involved into this field. And by 2008, 50% of TV market was on liquid crystal LCDs, basically. Like over 200 million TVs were made in those years. Okay? Like recently, this tablet computers, again, like a step, like Toshiba is producing these, a step again in these liquid crystal displays. Okay? I'm really not in this field. So like if you search under Google, you will more or less find the same things that I did. Okay? You can find a lot of information on what is going on. We always like use devices like liquid crystal displays, like computers, digital watches, DVDs, CDs, like there is a whole technology there. From chemistry point of view, like the rest is all electronics basically. From chemistry point of view, you have to make those right molecules. Like molecule is the starting point. If you have the right molecule, you can basically get this market and you can make better TVs or better displays basically. I just put a simple diagram just to show you how these LCDs are made. This is like a one single pixel. You have a reflective mirror. This is just a mirror. That's not really important. You have the polarizer, like in the microscope. This basically, like these lines, these yellow lines, are showing the direction of light coming from this polarizer. And you have a glass, and this glass is special, like regular glass. They are rubbed with a polymer, but this rubbing direction is important. This rubbing direction, in a way, they are again parallel to this polarizer. In a way, when you put the liquid crystal, this is the first step, first molecule, how this first molecule will align. That will determine basically the first layer of this liquid crystal. And there is a thin layer of an electrode. Basically, this is the negative pole when you apply the voltage, basically. And you have the liquid crystal here, and you have the second electrode. Okay, these are two basically metals, and you can apply voltage between this pixel and that plate, and you can align certain molecule in that region, and you can make no light go through. Like in the outer display, you have this is the light region, this is the dark region. You can write something there by just playing with the voltage between those two electrodes. In a way, you can make these liquid crystal molecules either align or disordered. Disordered, no light goes through. If it is ordered, certain light comes out. Okay? And on this side, again, you have this glass, same glass, but this time it is put perpendicular, like perpendicular to this one, the same glass. And you have again polarizer, but this time it is put perpendicular again, crossed basically. And this last glass is basically telling the orientation of the last molecule. So you have a molecule, you orient it, and you have the other molecule oriented perpendicular to that. Okay? In between, basically, if you go through, like when you, if you don't have any voltage between those two electrodes, basically, polarizer gets the polarized light. This is the light. It goes through this glass, senses the first molecule. Molecules are oriented in a way, it is rotating to get this orientation, and at the same time rotating the polarization direction of the light. In a way, light comes out. No voltage, light comes out. When you apply voltage, these molecules are all aligned in a way. It doesn't care about what the light is doing. Like basically, light is just going through the same polarization direction such that this analyzer is stopping light to go through. Okay? You have to basically switch the polarization of the light in a way to get through this analyzer. Basically, no voltage, there is a light, voltage, there is no light. So you can make light dark. You can switch by playing with the little voltage between those two plates. Again, you have whole technology. These are all like basically have some sort of liquid crystals inside and working with this principle. And this cholesteric ones, like these are the orientation of the molecules, and these molecules are a little bit special. In a way, in the second layer, it is rotated a little bit, rotated a little bit, rotated a little bit. In this top layer, they are exactly as this one. And when this repeats twice, you have a single wavelength, basically. This distance is in the range of visible light, such that if you send this gel, when you shine light into this gel itself is colorless, but because of this diffraction principle, white light goes in, all the color goes in, only one color comes out. All others are basically constructively, destructively interfere with each other. Only the one related to distance comes out as a bright light. You send the white light, maybe you get a red light. You send the white light. You can play with this distance by temperature or voltage. In a way, you can change the color of these materials. Similar to photonic crystals. Again, in photonic crystals, these are solid materials. You send the white light. These solid polymers are large enough in size such that it does the same trick, basically. You can put the white light in and get color from those. Like, I don't know, in nature, you can see examples like butterflies. Butterflies, some of the butterflies have really bright, bright colors. It is not because their wings are colored. It is because their wings are structured in a way it lets only, like if it is blue in color, it lets only blue light come out, such that those comes out, like when it goes through the structure, it goes, bounces back and forth, intensifies by this constructive interference. In a way, certain light comes out as a bright, bright light. That's why those butterflies have very sharp, nice colors. It is not pigments, colored material. These are all structure, basically, in there. And like I just put a little bit art in there, like when you look at the under microscope, you see all these textures. Like these are all light version. When there is light go through, you have structure in there. I think this is an example for cholesteric phase. Like all these details have some physics behind. I will not go through, but you get pictures like those. You cannot really draw these. These are naturally happening under the microscope. When you look under the microscope, you see a whole art in there. Let me go, more examples. And some more, like look at this one. Quite interesting, like all these features, all these spots, like we call it defects. There is a whole physics behind again. I will not go into, but you have an art in there under the microscope, basically. Let us come to what I do and the lyotropic liquid crystal ones. And these are the phases, like these are the molecules again, but this time I will call them surfactants. Surfactants are the molecules that we use in soaps, like in cleaning and everything. These are special molecules. And they show phases similar to what I showed you before, depending on the temperature, pressure, like in thermotropic ones. But this time, you need a second component, like if I have it there, solvent. And the common solvent is water, basically. Like if you take these molecules, put in water, they show these behaviors, okay? And when you look at the physical, these molecules in the presence of that second component, they self-assemble, they organize themselves without any force, basically, into some structure. I will call this as the primary structure. In the previous example, primary structure was a single molecule. Here, we have molecules, they are forming some sort of a structure. This is the primary, and these primary structure is assembling like in liquid crystals and showing this liquid crystalline behavior. They self-assemble into supramolecular structures or mesophases. When you look at the physical properties, you can see a lot biology in there, like have interesting interface with biology. I will show you cell membrane, for example, as like cell membrane is a liquid crystal actually. Okay? And the understanding of these properties has been relevant for improving like technologies like cosmetics, soap industry, food, crude oil recovery, detergents. Like it ends in the literature like this, but of course there is more. You can design materials. That's what I do actually. Like we use these phases to design materials that you cannot do in regular ways. Okay? And when we look at these molecules, you have these molecules have two parts. This part, like when you see anything zigzag, these are like CH2, CH2, or hydrocarbon. They do not like water. Okay? They are hydrocarbons. They are like oils. Like if you put a drop of oil in water, they always phase separate. They never mix. And this is the part hates water. And you have a second part. Usually this is the charged part. They like water. Like when you put this molecule in water, if you put certain amounts, they first go into the top layer of the water. It coats the surface as a single monolayer and basically seals the water. When you put more and more, it starts diffusing inside the water, start aggregating, that I will show you later. And if you look at more example, here you have a sulfate group, negatively charged ion. You have an ammonium group, positively charged ion. In some cases, this is again hydrocarbon, but a lot of oxygen in the structure. That oxygen makes these group polar in a way they like water. Basically, you always trick here in these surfactants. You have an organic group, you have a polar, like water-hating group and water-loving group, you can say. That's why these works in cleaning, because this part cleans all inorganic impurities. This part cleans all the organic impurities. In a way, that's how they function. You can put both negative and positive. All sorts of surfactant exist, basically, what I'm trying to show you here. And these molecules, like in aqueous media, for example, they, like when you reach a certain concentration, they start assembling into these type of structures. This is the primary structure that I am talking about. And these primary structure can be spherical or rod-like. Remember in the previous one, there was a single molecule making rod, but this time this rod is made up of many molecules. These spheres are the head group, polar group. The inside, like hairy part, is the tail group. And when you put in water, basically this hairy tail, the one which doesn't like water, is trying to hide from water. They go inside, and the water-loving group is trying to go to the water side and forming these structures. These structures, depending on the size of these molecules, they are tiny. Like this scale is 1 nanometer only. Okay? You create objects, this primary object, in the length of like few nanometer only. Okay? When you put more and more or reduce the solvent amount, these rods start assembling together into some structure. This is the liquid crystalline phase, basically. These rods are made up of those surfactant molecules. They self-assemble together to form these rod-like micelle, and these rod-like micelle come together to form this liquid crystalline phase. Okay? And here, like in between these rods, basically you have the water in this example, water molecules. You can do a lot of chemistry there. Like in this tiny space, few nanometer space, you can do chemistry. And this is the case if the solvent is water. If the solvent is in an organic molecule, you have the reverse case. The polar groups are hiding inside, non-polar groups are opening outside. Okay? You can do a lot of organic reactions here, non-polar reactions, polar reactions in those sites. Okay? Like more examples there. And again, the biology, like when you look at membranes, these are double helix. Again, water-loving site on this side, water-hating site inside, and you have a double layer. This is the cell membrane. And this layer decides the whole life, basically. Like this is the brain of cell. What will go in, what will come out from the cell. So again, those are those type of molecules Like this is phospholipid, for example. You have a phosphate group, a polar group, basically on the outer side, and inner side and outer side. In between the layer, these tail groups. These groups hates water, basically. They hide from water. And this is the other component of these membranes. And as I said, you can make chemistry there. Basically, you can do chemistry in those regions. If you put chemicals that polymerize and goes into solid state, and basically put in between those domains, you can get materials that you cannot make by any other means. What I mean by, if you put, like for example, glass is a silica. If you put molecular glass, which dissolves in those media, they can go on these domains because these are the ones they like, and they start polymerizing in this region and getting rigidified. This material to start with is a soft material. When they go and polymerize in those regions, they become solid. And you can basically burn these surfactant out, get a template of that. Like this is a TEM image of a silica. These white spots are those domains which are burned out, and the darker domains are silica, glass, what we know. But you have holes in these glasses, regular holes going through the glass. And these holes are in the range of the size of these, like you can tune between 2 nanometer to 50 nanometer. There is no like technology that can create this small. Like current technology, those expensive electronic technologies are in the range of like tens of nanometer. The best, the smallest and smallest are typically in tens of nanometer. You can go down to 2 nanometer here. Chemistry can do this for you, basically. These assemblies, you can modify these regions, solidify these regions. You get those solid materials in between those domains and burn the surfactant out because these are all organic. They can be easily burned out. You end up with a material with holes inside. And these materials you can picture as, like if you have a spherical box filled with test tubes. You all know test tubes, right? And if you look at from one angle, you can see holes, right? And these holes are large, we can see. Here, we have a hole, like we have a tube basically. Thickness of this glass part is only 1 or 2, 3 nanometer in size. And the opening, the hole in these tubes can be changed between 2 and 50 nanometer. Okay? Tiny, tiny tubes that you can do chemistry inside those tubes, like in our test tubes. You can put chemicals in there and do chemistry there. You can modify the surface, like you end up with a very, very large surface area. Look at this number. You have a 1 gram of glass. 1 gram of glass probably have few centimeters square area in regular way. But here you have 2,000 meters square. Almost this is like a soccer field. In a very tiny powder, you have a field inside that you can modify the surface to make catalysis, to make many applications basically, and use this surface for something. Okay? And by playing with this surfactant chemistry, you can play with the outcoming material. These are like fibers. And in these fibers, this is a single fiber, you have channels, those holes, going through from one end of the fiber through all the way to the other end. And those holes, like tunnels, can be as small as few nanometer, okay? Like extremely tiny. There is no technology you can drill these type of holes in these materials. There is no such, like even most advanced technology cannot do this. But these molecules can assemble these structures in a way, and these structures which are resistive to heat. When you burn the organic out, you end up with tunnels in these. And these days, people start using these for like modifying the surface for catalysis, for example, modifying the surface to put drugs inside. They can put the drugs and let the drug come out very slowly, slow release drugs application, many application anyway. And this is the picture basically. You have the rod, basically this fiber, and in this fiber you have holes like those running through. Like in certain type you can make these tunnel run through like helicals, depending on the type of surfactant that you use. That will decide basically. Like this is what we do actually. As I said, these surfactant molecules have non-polar and polar groups. Like I don't have too much time. I think how much time I have.
We have 5 minutes. People can leave if they need to go, but we can carry on.
Okay. Like as I said, these molecules in lyotropic phases, you can go, lyotropic phases needs a solvent, and this solvent was water, simple, basically, nothing is in there. And when I first came, I was trying to put metal in those structures because the metal is good for many purposes. Water is nothing, basically, boring. When I came, basically, I said, we have these salts which has water in their structure, internal water molecules. This H2O is a water molecule, and this is a metal salt, basically. Each metal has 6 water surrounding this metal, and you have this nitrate ion, basically balancing the charge. Can we use these to make liquid crystals? Like it sounds very odd to start with because salts are solid, and this is like a paste. When you mix those two, how they will go into this gel phase. Luckily, they did. Look at these. These are the colors of these metals. They form nice clear gels, and they diffract. They basically show all the behaviors of liquid crystals. That was the first discovery that salt can be used like a solvent. Solid can be used like a solvent, solution, basically. Okay? And that's what highlighted in Angavanta Kimya that year. I think this was the first paper in Angavanta Kimya from Turkey. Okay? So like you mix those two, you get these surfactant molecules organized as like tubes, and in between this polar region, you deposit these ions in there. These like yellow, green dots are like ions, basically. But these ions are not in the core. These are water-hating sites. So those ions cannot go in there. So you are confining those ions in certain domains of these structures. They form nice gels. And later like as I said, like when I look at the history of science, those progress going from one state to another was taking tens of years. After 10 years, maybe a little more than 10 years, we discovered that those salts are going into a melt phase and behaving like any other solvents. They melt when you put them in such a small space. This is called confinement effect. When you reduce anything into small, their melting point drops drastically. Okay? Like anything small melts easier. Like anything small, what I mean by small, few nanometer I'm talking about. Bulk materials, anything we see is larger than micron. Okay? But micron is like 1,000 times larger than these nanometers. Okay? As a result, if you can put those, they go into liquid phase. And we discovered that those salts ions are liquid and organized and surfactant into these liquid crystalline phases. Then we realized, oh, these solvents may behave completely different than those water molecules, such that under the microscope, we start heating. This is the 25 degrees. This texture is an indication of liquid crystal. Then we cool it to -10 almost, still there, nothing is happening. -20, nothing is happening. -101 degrees. We go all the way to liquid nitrogen temperature. Like texture is still there. At some point, this region becomes solid, goes into solid phase, but keeps the structure, never leaches out these salt molecules. Like if you put any salt in any solvent, if you cool it down, it will crystallize. Here, when you put in such a small domain, their melting point drops drastically, such that it never melts, it never crystallizes, it never freezes. Basically, these materials are stable down to -55 degrees. But this took almost 10 years. 10 years, we published lots of papers without knowing what the salts are doing there. Okay? And this was the first phase diagram of the system, basically. All these regions are the liquid crystalline region down to very low temperature. And this is the salt composition. This is the temperature, basically. This is maybe the first example of a liquid crystal that keeps at very, very low temperature. You can use these in maybe in North Pole for certain purpose. Anyway, I will go very quickly on this one. And when we discovered that, we said that this field is not limited with those transition metals with these water sphere. We can add that extra water into these type of salts. Lithium is very important in ionic conductivities for ionic membranes, basically. In this cover, we basically discovered that lithium salts also form liquid crystals. You can form gels. And this is a small application, basically. Maybe I can stop after this. You see, the middle region is going from blue to white, blue to white. This is 2 electrodes. I will explain this and I will stop. This is 2 electrodes, 2 glass, basically coated each surface with a conducting solid material. It is called indium tin oxide, transparent conductor, basically. And on the surface of this conducting electrode, 2 polymers are coated on each side. And you have to oxidize and reduce this polymer to get color. And to do that, you need electrolyte in between. You need an electrolyte. This can be, you can do in solution phase, basically, to switch the color. And our electrolyte was working perfectly fine. I think these conductivities that we get from this phase is the record high in these type of systems. They are extremely good conductors. And you can use for these type of displays, maybe not displays, but electrochromic devices and so on, as a conducting membrane electrolyte. Okay? We also work on the electrode sides, maybe I don't have time to show you those. We create those, as I said, glass coated with a conducting layer of indium tin oxide. We can make these colored materials, solid materials, as electrodes. Basically, we can also do the electrode parts as well. Okay, I will stop there. Our work also got some other covers. These are the few books. I mean, if anybody is interested, I'm sure we have those in the library. Anybody who is interested in liquid crystals, they can go through. And of course, the students, teamwork. These are current students and past students and the grants. And thank you for listening.
Next time I put salt on my food, I shall think it's a little bit more complicated than I realized. Yeah. Well, okay, we have time for maybe a couple of questions if anyone has anything to ask. As I said, it is time if you have classes or something now, but okay, we have a man here.
Do these crystals represent some distinct electromagnetic?
Yes, they do. Like you can align them electrically and magnetically as well. People are doing chemistry there. For example, they align these in a way, they can put a polymer in there. They align in a way, and when you get this soft material out, you end up with a solid template replica of what forms there. Okay, they can align solid materials that you cannot align by electric field or magnetic field through these liquid crystalline phases.
So yeah. Some magnetic resonance imaging applications are possible like this?
I don't know that kind of application, but maybe. It depends. You have to dream up, basically, that if this is useful, you can put those in there.
Besides the 2 fundamental categories of liquid crystals or mesophase that you showed us on that family tree, do you think there may be some more that haven't been discovered yet or could be synthesized besides those?
Yes, definitely. Like there is, like when you look at the thermotropic field, there is whole organic chemistry there. People are constantly synthesizing new organic molecules to make it better, basically. Okay? Like not every organic is showing these behavior, even though you may get the right shape. But if the forces between those molecules are too much, then you lose this property. They go either solid. If the forces are too much, then it goes to solid phase. Okay? These are all related to forces between these molecules. Like here, we are talking about very little small forces that even room temperature can make them move around. Okay?
Okay, thank you again, Professor.
Thank you.